Hello everybody and welcome to CS302. This is going to be the first official video of the class because this is the first official content of the class. And so, let us begin. Okay, so we are going to be taking questions from the people that are here live for what we're going to be reviewing. And so, so far we have suggestions for operator overloading. And I am going to try to stop about 4:35 for 44:35. So, you also remind me for those of you that are here in case I missed that. So operator overloading, the disk pointer, any C++ related things we'll be using in assignment 1. Maybe vectors. Actually, no, you don't really use vectors in the first assignment. You use those later. That's why I hope that you all started the assignment 1. I know at least some of you have, so maybe you can. You don't have to watch it live, Clara, but I'd encourage you to be here, but you can always watch it online. But hopefully if I do switch over to Twitch, it'll be clear. You didn't go over linked lists and templates. I can definitely go over templates. We don't need linked lists for the first assignment, and we are going to talk about linked list in general one of the weeks. So I could touch on some code for that one, maybe like the third week when we do that. So I'll skip linked list, but definitely I can do templates. You can set to grid view and hide participants without video changes. Oh, okay, yeah, you do what he said. Yeah, if you have anything that's just rough. Okay. So I think this is enough, but we'll see. Depends on how long this takes. So let's start with this pointer because operator overloading I have to actually refresh myself. But at this pointer I can come up just off the top of the bat here. So this pointer is useful when you are trying to refer to members of a class. And so let me give you some code as an example. So if you have a class A, and this class A has some variables in it, like an integer, a float, etc. It might even have an object, a pointer of class A in it, actually. We'll just call that a PTR, actually. And if you do something like that, you would want to do in your constructor a dynamic allocation for that, probably. And then in your destructor, you would want to deallocate it, probably. In case you don't remember, constructor would be that. That's your default constructor, I guess, if nothing's in it. And then your destructor uses this tilde sign, which is at the top of the keyboard next to tab key, above it. And that's your destructor, which again has nothing in it. But actually here, let's do that because that's some good review about allocating stuff. So you would do something like, actually, this would compile, but this is probably not a good thing to do in this scenario. Because the thing would crash basically after you run it, because if you do something here that says like a PTR gets new A, then when you run this code, the constructor is going to call another object of A, which will call another object of A, which will be like going forever, like Inception style. So that will compile. In fact, that's why if I had a variable in here that was like this, that wouldn't compile because it gives you a message something like you can't declare an object of the same class as the class you're in. Try it at home and see what the error is. However, that check is not done with dynamic stuff because if you're doing something like this could be like a linked list basically. You would be doing this kind of thing. So it doesn't do that check manually. So you probably do not want to actually have this code in here like this because this code will not run, okay? But so for now, let's just comment that out. However, in your destructor, you could say something like if aptr is not equal to null. Sorry, Python, gotta switch from Python world. If aptr is not equal to null, then go ahead and deallocate it by calling delete. Is that C++? Yes, I need just a closing curly bracket, and I think it's C++. And let's just move this curly bracket down. Okay? So again, maybe in here, what would be a good thing to do instead of doing this dynamic declaration would be setting it to null. That's constructors are a good place to initialize your variables in general. And best thing to initialize a pointer is to null unless you actually want to allocate it. Okay? So you have this class, right? So now, how do you handle this pointer situation? Okay, so when you have a function in here, so let's just say we have a function foo. And okay, this is actually a good review for me too. How do I declare this function foo outside of the class? You have to use a scope resolution operator, and then foo. Now, where do you put the return type? I think you put it here like this. Yeah, that looks right. Yeah, I think that will compile. But please correct me if I'm wrong. Can you have an if statement? So like a light change, like a light bulb went out. Can you have an if statement without an else statement? Yes, you can. In C++, you can. So this will compile. In fact, yeah, that's all I have to say about that. So yeah. Anyways, so here we have our foo function, and let us say that in our foo function, we would like, remember the whole private versus public variables, so this is a class right now, so any member function of a class can access any variable within that class. So this foo function can access b, x, or that aptr without having to put anything in front of it. It's kind of like in the same namespace, if you will. And so if you were inheriting an object from another class and that class was private, then you cannot access it. You can only access it if you inherit it as public or protected. Protected means that you can access it within the child class, but you cannot access it outside of the class, right? So there's a whole public versus protected, situation that you learn hopefully in 202. So anyways, if I would like to let's say foo's job is to set b to 0 and set x to 0 because we didn't do it in the constructor. So one way of accessing them is just to do something like b equals 0 and x equals 0. You can do that. Another way that you can do that, and I guess it would compile, although it's weird, is you could do something like scope resolution operator b equal to 0. So that's one way you could do that. And then you can also use this pointer. So you can say this arrow, or you can say this dot, and let's just say, what was that, x? Yeah, so we can do this x is equal to 1. We can also say this x is equal to 2. However, in the second one, you need that nastiness that we were talking about, I think, the other day. So with the reference operator like that. Okay, does this make sense? Is this readable? I hope. Let me make it bigger, actually. So the this pointer is useful to reference to reference member variables or member functions too, actually. You could access a function this way too, within the class. Although with functions, don't do that. That's weird. But definitely variables. Now, why would you want to do this? Well, let us say that because of your really bad coding skills, you decide, not coding skills, but bad coding etiquette, you decide to declare a variable called b in this function. So like you're like, yo, I'm going to declare a variable called int b in here and set it to like 42. Okay? Here's the issue. If I want to set b to 0 like this, when this is the scoping rules. What C++ does is it starts out here and it checks first within the local scope to see what b is. And so it's going to look within the foo function. So within this bracket all the way to the closing bracket of the function somewhere down there. Okay? And so because it sees the declaration right here, then it stops and it just assumes that that's the v you're talking about. And so if that's what you're trying to do, good for you. But if what you're trying to do is access the class variable, then this won't cut it. And so that's when you have to do one of these options, where you have to specify the scope like this with the scope access operator, or you can use your this pointer. So either of those should work in C++. Actually, this one too, technically as well. Okay. Actually, yeah. Okay. We'll leave this one with an asterisk because somebody should check it before trying it. I don't know if that one will work like that, but I think it should. But we'll let somebody try it. Okay. So yeah, that's one of the uses of this pointer. When you take CS326, they are going to talk more in detail about that, about like how it works when you're doing the call stack. So when you call a function with the call stack, what happens is that like the first address in that set of variables. So when you call a function, what it does is it creates an entry to stack, and then it sends all the variables related to that function. And by variables, I'm talking about the parameters. So it sends all the parameters in there, okay? And then it allocates variables locally for that function, like in this case, it would be B, any local variables, okay? But the ordering of that, the first, if you think of it like a list of variables that gets passed when you allocate a function, we can say this is parameter 1, parameter 2, parameter 3, and then you declare any local variables. So like B or whatever your locals are, okay? Local 1, local 2, and so on. This is if it's just a normal function. If it's a function that's part of a class or a struct, then technically speaking, the address 0 or the first address is not the first parameter. It's actually a pointer to the class. And that allows it to be able to access any of the class variables. So like in memory, it needs to know where the class variables are so that it can access them, because those might be somewhere else in the call stack, like up here. And so that pointer points to the beginning of the class. In fact, here's something that I used to play around with when I was better at C++ before the summer. If you do the dereference operator on a class, that address is the same address that you'd get from the disk pointer. And then you can get a little hackish with a class. So like, for example, if I get the address of this in memory, and this address is like 0x1112 or something, then the address after that is going to literally be 0x1116, because I guess it's 4 because it's an integer. So that would be there. So then even if this is like a private variable, and this is a public variable, so like if I were to write private here, and this is public up here, and like I have the address of this, I can access X and change a private variable, so I can hack in and change it. And that used to be an assignment in 202, that before we went to the team assignments for the whole instructor group, which is pretty cool, actually. And even if it doesn't let you, you can use reinterpretcast to get around that stuff. So you can hack your variables that way. So, yep. Why would you ever want to do that? Well, you have to know the source code to know the order of the variables. But maybe like someone's really just not letting you like change somebody else's code. So this is one way around that, if they don't want you to change code that's there because you might break it or something. So protected, or either protected or private, it doesn't matter. You can access it as long as you have access to one of them. And in fact, if you have access to the class itself, which you should if you're using an object of that, then you can use again reinterpretcast. What you do in that case is you literally code a struct that has the same order of the variables, so like an integer, a float, and then a pointer of that class. And then you make it a struct because a struct is public by default. And then you just reinterpretcast the pointer from a class to pointer of the struct class you made called fake A. Remind me sometime and I'll show you that code. Like I have an example somewhere. And then boom, you're good to go. Like you can access any of the variables, whether they're public, private, or protected. So yeah, fun times. Yeah, good times. Do we have to put an asterisk before the x if x is a pointer variable within the class while using this? Yeah, you do. It gets really nasty. So like if, let's say that you have an object, I'll just put it down here, but like, here, I'll just make another class. Class B. Let's just say that we have an int y like that. And if you're trying to access it with the disk pointer, then it becomes this y with an asterisk like that. And I do not think that you need to put parentheses in this case, but let's go with if it doesn't compile with this format, then put the parentheses, okay? Actually, to be extra safe, just put the parentheses anyways, call it a day. So yeah, I gotta refresh because that's the whole reason why you put parentheses in like scenarios like like this is because otherwise it prioritizes doing it through here. So I think you have to put those, but don't quote me on that. You know, put them anyways. If you put them anyways, then it'll work, right? They'll just be redundant if you don't need them. So, okay, so that's kind of the disk pointer. Like I said, you'll learn more about it in 326, but I don't think you really need any more for this class because, again, the only time you ever will need to use it is if you have a problem with your names, like here, where you're actually using, where you're declaring a variable with the same variable name as something in the class, and you have to use scoping magic to be able to access the class variables. This can all be solved if you literally do not make this variable called B. Like, just do something else other than B, because you have a variable already called B, and that's why you get that whole headache. The same thing applies if you have a global variable. There is a way to access global variables within the class, even if they have the same name. I believe all you do is just put this, so like let's say there's a global variable somewhere in here that is called like int g, and you're trying to access it from anywhere in the program, but you have other local variables called g. I believe all you do is do that. Like, you don't put anything in front, I think. Don't quote me on that, but I think that's what you do. You shouldn't be doing that anyways, because you shouldn't be using global variables, right? So, yeah. Yep, okay. So we're about halfway through the review time. So let's move on to the next thing so we can cover more of these. Templates and operator overloading. So for those, I would rather show you code, because we need to make sure this code compiles, because I don't trust myself writing the code without compiling it when it comes to something like that. It's been a while. Yeah, I'm gonna have to open up the VM for this. Then let me open that up. Let me open up the VM, and while that's opening up, I can show you some template stuff. So there's two kinds of templates. There's class templates and there's function templates, and you should know both because you probably use both in one way or another in any of the assignments that you do. Plus, in general, like, templates actually make your life easier, so you want to use them. They can get nasty when you have like templates inside of templates because things get really wonky when you're actually making your class definitions and whatnot, declarations. But you know, it's like anything. It's great until you do something really nasty and then it's not great. So yeah, okay. So let me pop here some operator overloading. And by the way, I did do the debugger setup in my 202 section. So that video is on Canvas on UNLB. So you can definitely just check that out, or just try to follow the link that I sent you all to set it up. Well, did I send it to you all? Here, I'll send it again just in case. I don't actually remember if I did. Yeah, for VS Code. Yep, this one. It's relatively straightforward, but in the video when I go over it, I explain some of the hurdles that I ran into, which is when you're trying to pick the debugger and the compiler. Like, there's like 3 options, and some of them work, some of them don't, and you just kind of have to experiment and you know, do it until it actually works, kind of thing. So okay, let me switch over to sharing the code. Cool. Okay, maybe I should zoom this in a little bit. Okay, very cool. There we go. So, is this operator overloading? No, it's not. But it is somewhere in here, though. Let's try this one. This one definitely is operator overloading. Okay. Okay. So I don't know if you're necessarily going to be using it in this class. I don't recall, like, you know, of course I can change things, but I don't really recall there being much usage of it. But it does make your again, both templates and operator overloading, but specifically operator overloading is good because it saves you time coding things. That's, well, at least that's the premise. The reason why it's not very popularly used in assignments is because it saves you time when you're coding like something really big, not like an assignment size big. So, you know, in the assignment, you code a function because you needed to use it maybe like once or twice, not like 50 times. So there's no point in really like optimizing it and that kind of thing. So that's why it's not as popular in assignments, but it's still good to know. So the trick with operator overloading is to use the friend function stuff. The Discord link is on Canvas on the first section or module on the references Discord link. So you can if you're able to be here, it's because you have the WebEx link, which means that you should be able to access that, and then you can go through there. But yeah, so with operator overloading, you need to know the function specific for that operator, which tends to be the word operator and then like the actual symbol that you use. So like a plus, a minus, an asterisk for dereferencing or for multiplication, I guess. Division, post increment and pre increment is kind of weird. It uses the plus, but it has special parameters, I believe. And so that's kind of all there's to it. So as long as your class has that function in it, then you can do the operator overloading. So, like for example, in this class, I'm trying to overload the subtraction so that I can subtract. And so there's two ways to do the operator overloading. One of them is to do it like this, where you basically have a member function, so it's not a friend function, and so you can use the left side of the operator as sort of the object that you're calling it on. And then your first parameter is going to be the right side. Now, what do I mean by that? What I mean by that is that, like, you know, instead of calling, so if you see this line, I overloaded the plus sign. Can you see that? Let me move it up. So right here, you see this, I have A1 plus A2, right? In theory, I am also able to do dot operator plus A2, like this. And this two lines, actually, well, let me do the assignment part. So like, A answer equals that. So these two lines are identical to the compiler. In fact, the top line becomes the bottom line when you're compiling. Do you have HTTP files anywhere for download? I do, but I need to make a link for the 202, for the 302. These are all like I just made them. I'm like, it's so sad. I actually made this live on 202 last summer when I was teaching it, I think, or maybe in the fall. But when I see these now, I'm like, wow, I don't remember coding this at all. But yeah, I can make this available. They all have a lot of examples. They are not labeled very nicely. Like this is called OP2, but they are labeled by number, which matches the lecture video. Because that was the idea, that you could watch the lecture video and then download the code to see it. So I'll make them available if it helps. Yeah. Yep, just send me a reminder because I will probably forget like tonight on Discord, and then I'll make it open. I'll put it on Google Drive and then post a link on Discord and Canvas. But yeah, so yeah, if anybody wants to label them for others, that's cool too. But yeah, like I said, they're numbered, so like this is what they look like, and each of these numbers represents a lecture in the summer. So like video 5 is 05. Actually, yeah, I think it's either a lecture or a week. It might be a week actually. Yeah, it might be a week. So this might be like 2 lectures technically. So then as you're watching the videos, you can look at this, but you can also just look at them as coding examples of how to do things. So like this operator overloading examples. So yeah, okay, just I will do my best, but just send me a reminder because I might forget to upload it. So yeah, okay. Anyways, so yeah, so basically the compiler converts this into this. In fact, I just noticed I have that example here for the minus right here. So like A operator minus A2 is the same thing as saying A1 minus A2. And that's literally what happens with every operator. And so that's what you have to code. So that's one way of coding it. The other way of coding it is using a friend function, which you have to do sometimes when what you're trying to overload is private for that class, such as with the cin and cout operators, which are the stream insertion and stream extraction operators, the signs like that or the signs like that. Okay, and so for those, a friend function, by the way, is a function that allows anyone to access it. So like, actually that's the wrong way of putting it. A friend function is able, as long as a function is friends with a class, it can access any of its private variables. So it's like saying, if you're my friend and I give you my house key, so you can access anything in my house. And so if you're friends with 2 with two classes, then you can access anything from them. And so what you do when you're trying to overload stream insertion and stream extraction is you use that friend function power so that you can be able to access more than one class. So if you're overloading an operator that only involves using a single class, then you can make it just a member function. But if you're overloading an operator that's going to be working with two classes, then you have to use the friend approach. So all you do is you write the word friend, and then you just write the operator type. In this case, it's OS stream because it's what the like cout returns is an OS stream, or like fout if you're doing overloading of the reading and readout functions, like the f streams. And then these parameter kind of things are things you just have to remember, like the ordering of these things. So I wish I could tell you, like, I mean, there's a reasoning for it. Like the left side should be the part that has like the cin or cout, and the right side is like when you say like, you know, cout hello world, and then you put again the stream insertion, and then you put like endline. Think about it. You put cout first on the left side of the stream insertion, right? So let me switch over so you can see what I'm talking about better. So like, if you have a line that's literally like this, cout hi, just like that, then this here is the operator, right? So it's a binary operator because you have something on this side and something on this side. As you can see, this is like not any generic variable. It's like a very special variable. It is a OS stream variable, and that's just something you just have to know, kind of thing. Why? Because if you're using file streams, you could do something like fout, and that's linked to your file, and then this is something to like write to a file, right? But it's the same operator technically. So that's why this is an OS stream variable, and it's passed like this because of like magic that happens because of things when you chain them together, etc., etc. So again, this is something you just have to know. This one on the other side, you know, is a string variable, but in this case, if you're trying to say cout of a special class, so our class A, you know, an object of class A, that's why when you're writing the code, you have to put that as a parameter, okay? So yeah, that's all I'll say for now. So when you say the friend will allow us to access the operator of class A, do you mean that class B can access class A's operator? No. What I'm saying is that if you're trying to do something like A plus B, where A, you know, they're class A and class B, and let's say that class A has an int x in it and class B has an int y, but those are private variables to each of their classes. If you're trying to add them together, you need to access those two private variables, but they're different classes. So if you put them on one of them, then you can only access that class as A. So if you put the operator overloading function in class A, then you can access the int x in class A. But if you're trying to open the one from class B, then you cannot access that. Let me give you a visual example of that. So you have a class A, and that has an x in it that's private, and you have a class B, and that has a y that's private, right? So if I'm trying to overload like the addition, and what I'm trying to do is I'm trying to do A plus B, where A is class A and B is class B, okay? So what I'm really trying to do is I'm trying to add x plus y. Like that's what I want this to do. So if I put my operator, like overloading, so the operator plus function, if I put that in my class A, so if I take this here and I put it here, then that's great because now I can access this x. But I cannot access that because it's private. Similarly said, if I take this and I put it here, then I can access this, but I cannot access that one. So that's when I basically say, okay, we're going to make a special function that's going to be a friend function to both this and this. And then I'm able to access the private of x and y. So that's why it's a friend function, and it doesn't have to be in either one. Okay? So that's why in the code here, we have listed this as a friend. However, the function itself, it's not member of neither of the classes, as you can see here. It's just a friend function. So it's just in your friends list. But in the class itself, it's not put anywhere else. It's just in your friends list. Okay? Sorry for your assembly pains. But yeah. Anyways, I have videos on operator overloading that are like one of the first few videos that I ever did online. So I recommend you check those out if you want to do more operator overloading practice. So the friend has access to both private variables from both classes, as long as you put Like, remember these things are your forward declarations, I believe they're called. Like when you're listing them on functions. So you put that in both classes you're trying to access. Okay? And as long as you do that, you're good to go. And typically you need to do that when you don't have access to anything on the left side. Because with the OS stream, you have access to it, but you can't like manually add friend to it. But you're not accessing anything private on that. But you can't put it in that class, okay? So yeah, like I said, if you're really confused right now, if you do friends, they will work always. Like friends will always work. Whereas like the normal version, where you're just doing members like this, will not always work. So I guess if in doubt, just learn the friends way and stick to it. Okay? What if they're not private? If they're not private, then you don't need to do a friend function. You can put that function anywhere you want, and it'll work okay. Like you could literally make it just a function that's not a member of neither class, and then you just make the thing work. So like it'll just work. I have examples of that in the videos too. But yeah, you only need it to be friend when you're dealing with privates. So if not, then you can overload. It's fine. Okay, we are hitting that time limit. I have not gone over templates yet. Let me very, very fast just open up a template example. I wish I could do more, but you know, we have to like do the actual class material. So here's a simple template. Yeah, this one. Look at this one. Okay, this is a simple template class. You write the word template. You write this less than or greater than sign. I don't know how vectors work. And then you put some variable that's going to be your template. And then if you're trying to make it a valid returning function, then you make it return that type as a template. So t add. And then this is literally just a small function to add two of these template variables. So it's like a templated add function. That's all it is. Here's an example where we have a templated function. Sorry, this is a templated function. I said class. This is a templated function where you're adding two different types. So we have a u and a t. They're not defined. They could be integers. They could be floats, whatever it is. So in this case, we're saying that the add function is literally going to multiply. Don't ask me why I did that. Probably doing it, making a case as to how not to do things. And then it's going to add this, and somehow magically going to return a t. Okay? You can mix templates and operator overloading to simplify code, which is what I'm pretty much doing here. That's why you see the operator overloading here. Okay? But just know that this is the syntax for templates. Let me open up another one. I know at this point I'm rushing, but we have to switch over. So I got at least most of the stuff done. Here's a class. Okay, so here's a class template. I wish I had one with just one template, but I have one with two. Okay, so you write the word template again. You say class u and t. These are just generic. These are just whatever you want them to be. You know, I just pick u and t for fun because t sounds like template. Okay. So the way you do it is once you declare them like this, then you can use them anywhere in your code. And what is going to happen is at compile time, nothing happens at runtime. At compile time, when you're making your declarations, in here you list what they are supposed to be, what type. So here, they're both integers. However, here, there's an integer and a double. And at compile time, it's going to fill literally the word int wherever you see the word u and t. So it's literally going to make this be a word int, this be a word int, and this be a word int. It's going to do that, and it's going to try to compile the code. If it compiles, you're good. If it doesn't compile, it'll give you an error with the templates. That's all templates do. It's all happening at compile time. All right, we got some questions. What are the pros and cons of using templates? You write less code that does more things for you. So like you only have to write, it's about writing less, more efficient code. When you have something like t becoming an integer, is it stuck as an integer if it's in the same object class? Yes. So once you declare this as an integer, like in this object a, lowercase a, then it'll always be an integer. However, if you make another object of the a class, but in this case I made the second one be a double, then it'll always be stuck as a double. And again, all of these checks are done at compile time because this code is already written. So it makes sure that this actually would compile if that is a double. Because like what might happen is like, let's say that instead of putting an int here, I put like some obscure class. Then when I'm doing this, let's see, what am I doing with it? Is there anything interesting? Well, let's say that in somewhere in here I said like t+1. And t is not something you can add because it hasn't been overloaded that way. Then it wouldn't compile. So that's why it does what checks at compile time. It's strictly to save you from writing the same, like, the idea of templates is you don't copy and paste like the same code 5 times for 5 different classes. You just make one class with templates and then you use it that way. That's the whole purpose of templates, is to avoid copy paste. Because copy paste is bad, because when you gotta update your code, you gotta update 5 of the same thing, and that's how you get errors and bugs in code. Would you need another template variable to become another data type to multiply something like a float? No, in this specific case it would work, but it's on a case-by-case basis. Again, literally what templates do is substitute. They're like kind of like a macro. They literally substitute the type at compile time. So as long as your code would compile if you literally copy and pasted the word int wherever you see t, then you're good to go. That's literally the hard limitation of templates. All right, that is it. No more C++. I do have videos also on templates, but there's tons of stuff. Geeks for Geeks, again, I highly encourage you to check that site out. Has examples on templates. Very, very nice stuff. So definitely check those out as well. Okay. Now let's actually learn 302, the class you're actually here for. Okay, so for that, let's use the iPad. Okay, so let's take a second to flush out of our mind C++. We're not going to talk about any programming language for a little bit here, okay? For you. For me, I got to teach 202 in an hour, but yeah. Okay, so far in your previous classes, at least in the end of 202, you started to learn about different ways of storing information, right? You discovered something called an abstract data type, so abbreviated for ADT. Abstract data type, okay? And so you have seen these, maybe not by this name, but you have coded them and you have done them in your 202. What am I talking about? Well, I'm talking about something like an array that maybe you use for specific purposes. Maybe a linked list is a beautiful example. If you got to do a stack or a queue in your 202, then those are examples. And so what does it mean? Well, an abstract data type is two things. It's a set of values and operations, okay? So we got set of values and set of operations. Now, what I mean with values and operations is this. Let's think about linked list for a minute, okay? And the double linked list would be also an abstract data type. Let's say that you're making a double linked list of integers. Your set of values are the integers that are stored in this double linked list. The set of operations that you have on this double linked list is going to be things like insertion, deletion, sorting if you have a sort function in there, allocating memory, I suppose, is an operation, although those are more like overhead stuff. But like when we really think about operations, we want to think about operations on the data itself. So probably just insertion, deletion, and sorting, okay? And also reading, maybe, like actually printing out the contents of the linked list. That's pretty important, right? Or indexing too, like printing out the fifth element of the doubly linked list. Or printing the double, or print, since it's a double linked list, you might want to try to print it backwards. Although you could do that recursively too in a singly linked list. Okay, so that's what an abstract data type is, and you've been using them without knowing them by this name. Okay, so let's now define a very, very important term this course, I suppose, and that's what a data structure is, because that's literally the name of the course, right? So maybe that's a good place to start. You know, I'm surprised nobody has asked yet, like, why is this course called data structures? Well, a data structure is actually nothing more than implementation, aka C++, of an ADT, of an abstract data type. Okay? So this course is all about implementing these abstract data types that I'm going to show you, which we also just say these data structures. Okay? That's like, I would say 80% of the course, because the other 20% are some algorithm stuff, like sorting and extra shortest path and whatnot. But a lot of the course are, especially all the tree stuff, is literally me teaching you, you know, these things that have operations and values associated with it. And now instead of saying things, we are going to say abstract data types or data structures, okay? Because me saying to you like, okay, this tree has this and this, that's like extending an abstract data type. Me telling you like more of like how you're going to do it in actual code would be the data structure side of that, because you're implementing. In fact, your assignment is the data structure part, whereas the teaching lecture material is the abstract data type. So you have to go from this to this. So you have the thing like step 1, step 2, question mark, and then your assignment is your profit because you get that good grade, right? That question mark is going to involve you trying to make the code work, of course. Okay? So now that we talked about what a data structure is, let's talk about what makes a data structure good or bad. Okay? And what we want it to do, like what kind of operations we want it to do. Okay, well, again, we all should know a linked list, so that's why I'm using that as an example. That's kind of why we cover that in 202, so that like we literally have something to talk about in this class before, like, because otherwise I have to teach you what linked lists are before like I can actually start explaining these like meta ideas, right? And so the main things that we care about with a data structure usually are being able to insert data in it, being able to retrieve data, that's to access the data, and then it's also very useful, especially in today's scary world, to be able to delete data. You know, we don't want to keep there anymore. All right? In addition to this, it's also nice to have the ability to modify data that's already there, which is really a combination of these three things if you think about it. Because if you're able to insert and retrieve, then you can retrieve data, play with it, you know, by modify it, and then insert it again. And then, or you can, if you want to take something out, it's a mixture of retrieving and deleting, right? You have to first retrieve, which is you have to find what you want to delete, and then you delete it. Okay, so modify is kind of like a combination of that. Similarly, when we say something like process data, it's a combination of that, but it's its own thing. Process could be things like sorting, but these are kind of like interchangeable terms as well, okay? So these are the main sort of purposes of a data structure, okay? So, cool. All right, that's what we want a data structure to do. So how do we pick between one data structure and another one? How do we pick between a singly linked list or a double linked list? Like what makes one better than the other one? Well, it all comes down to these very like epic sounding things: space and time. And these are really the important words in this class: space and time. Okay? What is space and what is time? Well, you know, I'm not the right person to ask like that deep of a question, but I can tell you, at least in the sense of data structure, what I'm talking about: space and time. Let's think about it. We have a limited lifespan, right? I think we do. I don't know. I'm still alive, so I can't prove to you that we don't. But yeah, we have a limited lifespan, right? And so when we want something done, we preferably want it to be done within a given time period, right? If I would like to say, hey, you know, you tell somebody like, hey, can you go and clean the kitchen for me? Or can you go and vacuum my car? Or can you go and clean my car? Or, you know, you take your car to like a car dealership or car repair place, and you say like, hey, how long is it going to take to fix my car? Or how long is it going to take to reset my password? We're all interested in time, because time is very valuable because it's limited, okay? When it comes to computers, time is something that computers don't care about, because, you know, they don't have that concept of time really. So it's up to us to be able to gauge whether something is fast or slow, right? And so when it comes to a data structure, we have the concept of insertion, of retrieval, and deletion. And these things are controlled or limited by their speed. Some of them are slow, some of them are fast, right? For example, let's say you want to sort a list. You all learn bubble sort in 135 or 202, right? If you want to sort a list, and if not, I guess we'll do bubble sort, but like, I really hope you all know at least bubble sort. But yeah, if you want to sort a list, it takes a long time with bubble sort, right? So I would say that's a really slow algorithm. This semester, we're going to learn algorithms that are pretty fast. In fact, they're at the theoretical limit of how fast something can be when it comes to sorting. Those things are things like quicksort, timsort, which is a combination of all the sorts, and they're much, much faster than bubble sort. So if all you care about is time, then you would want to choose specific algorithms over other ones, okay? So That's where time comes into play. And in this class, the majority of our algorithm analysis and asymptotic complexity and whatnot is going to be focused on time. Because time is, back in the day, space and time, like, were, I would say, both as important. But in today's world, I think that we've gotten to the point where, at least for computing, time is the one that we care about the most. We still care about space. I'll give you examples of where space is like, okay, this is a little too much. When we do like a hash table and we talk about what a direct access table is, that's one example where like space is actually like a thing that's an issue. But nowadays, time is the big one. Okay? But let's talk about space. What do I mean by space? I'm not talking about like outer space. I'm talking about space when it comes to storing the data, right? When you're inserting, retrieving, or deleting data, that data has to be placed somewhere because, you could have an insertion and you could even have a deletion, but if you're not able to retrieve, you might as well just be throwing things into the void, right? You've inserted them, and I guess you can delete them because they're not there anyway, so yes, you've deleted them, but you can't retrieve them, right? So in order to be able to retrieve data, it means that you're storing it somewhere. Now, this might become as trivial as like, well, okay, if I got 10 numbers, then the space that it takes to store 10 numbers, like, is something that like is fixed, right? Okay, let's say 4 bytes for an integer, 4 times 10 is 40 bytes. So bam, as long as I got 40 bytes, then you're good to go. Well, yes. However, it turns out that these two things are intertwined, space and time. Basically, sometimes giving more space to something will make it faster. Perfect example of that is hashing, okay? So sometimes things that require a lot of time don't require a lot of space. And sometimes things that require a lot of space don't require a lot of time. So these things are not completely opposite to each other, but a lot of the times they can be. And so that's the other side of the coin. When you're storing big data, and I'm talking like big data, like Google or something, if you want that data to be retrievable quickly, it's not going to be enough to just dump it in there. At the very least, you would want to sort the data because by sorting the data, you can access it quicker. But you will probably want to index the data, you will want to hash it, put it in the dictionary and things like that. And those kind of storage things that speed up the time tend to also increase the space required to store the data more than just like literally putting it in there. Okay? So while, storing the 10 numbers unsorted somewhere is going to be slower than storing the same 10 numbers with the same amount of space used, sorted, is going to be faster. Those are situations where the space will not change, but by doing it in one way, it's going to increase the access speed time. There are other scenarios where it would literally make a difference if you give it more space. It will make it faster. In addition to that, there's a catch. Think about that for a second with sorting. Sorting something makes it faster to access because you can use something like binary search to access it faster. However, the act of sorting something is not something that is free. It takes time to do that. So now we also have a competition between these three sort of groups. Things that insert quickly. So if we have an algorithm that inserts really fast, for example, a linked list, you can just append very fast, no problem, whatnot, may not be as fast to retrieve or delete. On the other hand, something that, let me leave that out actually there, something that you can insert and it takes a long time to insert might be faster when it comes time to retrieve, and maybe when it comes time to delete. An example of that is, an example of that is like if you're inserting a sorted linked list or a sorted array. If you're inserting a sorted array, it's much faster to access a specific item because you can use binary search and then get there pretty fast. However, inserting it sorted takes more time because it has to figure out where to insert it. We'll see that when we do something like insertion sort. So hopefully these are some examples that give you an introduction as to the why we care about the space and time of an algorithm. Okay? It's no longer, in 135 and 202, it's enough that something works. Not anymore. Now we've gotten to the point where whether or not something works is not good enough. Now we care about whether or not it works fast and it doesn't take the entire space in the world to store it. Okay? we start to actually care about if the code that we write is something that is going to actually run in a within our lifetimes, yeah, or better yet, within our patience limit. Okay, so when it comes time to measuring units for time, some of the things that you should keep in mind is that seconds is cool, but not very good as a metric, because my computer is maybe faster than yours or slower than yours. And so what might take my computer 10 seconds to run could take yours 5 seconds to run. And we could be running the exact same algorithm. So it's not necessarily very good as a way of measuring speed of an algorithm. Okay? That could be like, oh yeah, I created this like really good algorithm to sort stuff. It takes 1 second to sort 1,000 numbers. And like, I ran like the state-of-the-art algorithm in my Windows XP machine behind me, and it took 30 seconds. So clearly my algorithm is better. Yeah, no, it's just a computer. Like, come on, man. Right? So basically, seconds is not very good, but it's one way of measuring things. You can also use clock. Clock is going to be like your computer clock, like your gigahertz and whatnot, because then you can see that. And that's kind of a little bit too picky. So a good middle ground is number of operations. Okay, or operations per second, you see that too, but really we care more about the number of operations. Okay, so when it comes to showing you sorting algorithms, we will measure something in terms of time or speed based on how many operations are required, as in like how many swaps, how many comparisons. That's what we'll actually define how fast something is. And then of course, if a computer can do those faster, then that's great. But again, we're just trying to see something that is separated from computer speeds. We want something that is pure, so that we can really compare algorithms without it affecting the hardware and whatnot. But don't get me wrong, especially with parallelizing, things can change a lot, because like running quicksort, which is really fast, in a single core machine, will be okay, but like will be beat by running merge sort on really big data, by the way, not like small data, on really big data, but running merge sort on like a multi-core machine or like an entire like supercomputer like center that can like distribute the load between different nodes. Merge sort is more parallelizable, and so that might finish way faster than quicksort, just for that simple fact that you can parallelize it. So that's a whole different level, and you learn more about parallelizing in 370 and whatnot. But that's just a little warning about that. When it comes to space, that's a little bit easier, since we're all computer people by now. So we can talk about that in terms of like bytes and whatnot. So for our computer, what we care about are things like main memory, RAM, and then secondary storage, which has really increased in speed in the last few years. Back in the day, this was just like hard drives, but now with SSDs and things like M2 drives, cool stuff. You can run things really fast. I don't know AMD. I'm part of the Intel club, fan club. So yeah. Okay. So yeah, that's space and time for you. Okay. So moving on, let's talk about another fancy term that we will be discussing, and that is algorithm analysis. I think I spelled analysis correctly. Okay? So one of the things that we're going to be doing in this class is we're going to be looking at these algorithms. Some of them you already know, some of them you will learn, and you better learn them for the test. Thank you. And then and we're going to be looking at the things like insertion, deletion, and retrieval, right? But even then, by trying to use our units of number operations, it's not enough to be able to like mathematically analyze these algorithms, okay? And this is where we are going to be introducing the asymptotic complexity of something, okay? Now, you all remember from math class, when you have a graph and you have a line, this line is called f of x, right? And that f of x in this case, maybe it's like 1/2 x Yeah, that sounds about right for this line because it's kind of flat, you know. However, if you have if you have something like this, what is this one? Let's call this one g of x. That's probably going to be something like x squared, right? And I guess since we're looking only at the positive side, then we could you know, we can put one of those in there. But whatever. For now, just ignore everything other than the positive, you know, the positive axis. So yeah, normally when you're writing a function, yes, you do something like f of x is equal to mx plus b, where this is your slope and this is your y-intercept, right? So this is all math time, okay? So what we're trying to do here is we want to make a graph of how long a algorithm takes. And by the way, what I'm about to tell you is really going to bias towards the time side, but it all applies to the space size. We just exchange more operations for more bytes used, basically, okay? More space used, more numbers, whatever your unit is, which is typically based on, if you're sorting, it'll be a single number, or if you're storing data, it'll be a single piece of data, okay? So again, we're gonna stick to time for now, but all the stuff I tell you basically will apply to space, okay? So, going to this, let's talk about an algorithm that is linear time, okay? So what does it mean when I say an algorithm is linear time? What I mean with this is that an algorithm, the growth of the algorithm when you increase the number of data that you have to process is going to be a linear relationship between that amount and the time it takes. So if I say that I can process one operation per second, okay? Or actually, let me change that. Let's just say it takes. What's a good way to say this? I don't like using the word second. So let's just say that for 10 numbers, we'll call it 10n. You know, it takes 10 operations. Okay. But if you have 100 numbers that you got to work with, it takes 100 operations. Okay. This is a linear relationship. Okay. Let me give another example. Let's say that I have 20 numbers. It takes 200. And then let's say the 40 take 400. Is this one linear as well? Yes or no? Chat. Yes. Very good. Yes, it is. Indeed it is. Except this time around, the linearity is that, well, this would be something like y equals x, basically. This one is no longer y equals x. Or I guess actually, because somebody said y equals mx will be, but I like to use f of x is equal to x. Okay? This one is no longer f of x. This one is technically what, 10x? Right? So this one is 10x. So it's still linear because it's a linear number here, but now that this slope is no longer just 1. It's a constant, and the constant happens to be 10. We'll say C for constant is equal to 10, right? One more example of that. Let us go ahead and say that, I'm like thinking these on the fly, so, you know, give me a chance here. 40n is equal to 410. 80n is equal to, yeah, that one, okay? So in this scenario, what am I gonna put there for f of x? What is this one gonna be? So it's gonna be something here, x, right? 10x plus 10, very good. Is this still linear? Yes, it is, because there is no power here. When you know it's not that's something like square, that's when you know it's no longer linear. Now we're talking quadratic, but it's still linear. So now we have this BD part. Some people call it bias or y-intercept, whatever. And then you have your slope, right? And so if we're graphing that, it would look something like, you know, it's not to scale, but let's just say 10 is here. So then it's going to look something like that, okay? Probably more steep than that. Something like that, okay? Let's just leave it like that. It looks prettier, okay? And so these are linear relationships. Now, what a quadratic one would look like you know, whatever something like curve like this would look like, basically. So you know, it would be like, let's just do like x squared. So maybe 10n becomes 100, whereas 2n becomes 4, and then maybe like let's do one more. So like 7n, 49, right? So that one will be something quadratic, and there could still be a bias at it. So let's just say you add like 3 to each one. So then this actually becomes 7. This one becomes 52, and the last one becomes 103, right? So that one would be something like x squared plus 3 for that, okay? So hopefully this math review is all easy for you and you all remember this. Fingers crossed. Otherwise, we're in for some rough times. So great. This is all great, right? We know now how to represent, at least, you know, well, you only see 2 examples, but like you're getting an idea of how to represent something of an algorithm mathematically as a graph, right? So what you really have to do to be able to do all of this is to be able to identify, I'm looking for it, or I guess it was this stuff. You're trying to identify this relationship here between the number of data and the operations and how that changes on your algorithm. What we're saying is that like there's some magical algorithm here. Nobody knows what it is. Big mysterious algorithm. This is a black box, they call it actually. You have a black box in there where you're feeding it 10 numbers and you're getting the result you want, and you're counting the number of operations it takes 10. You're feeding it 100 numbers and counting the number of operations it takes 100, right? Or in this example, you're feeding it 40 numbers and then some magic is going on, and then you get your answer and it took 410 operations, okay? Or 810 operations, okay? This black box, like you don't know what is happening in there, but that you know how many operations it took. Again, I'm using the word operation because it's not good to use seconds, because again, seconds is something that is going to depend on physical world, whereas this is like strictly theoretical stuff, okay? So, you know how to plot these things, okay? So, now comes the part where like you want to impress your friends and say like your algorithm is better than theirs. How do you do that? Well, if you're plotting the lines and your algorithm is this and their algorithm takes this, actually, let's do more realistic. Let's say your algorithm is that is this and their algorithm is this, okay? So that's Joe's algorithm, and this is Jane's algorithm, okay? Just from your intuition, which algorithm is faster, less time? Jane or Joe? Jane. Very good, Jane. That's right. And that's very important that you understand. Now, if anybody was thinking Joe, let me explain to you why that's not the case. This is number of operations. And this here axis is the number, the number of the data that you're working with, okay? So what this is saying is, even if the amount of data that you're working with increases, so like you feed your algorithm more data, it's not taking more operations to run. So it's pretty efficient in that sense. We're saying that, let's say here, right here, this is like 100. We're saying that even when you're feeding it 100 numbers, maybe this is 20. It's 20 operations, whereas over here, it's more like 50 operations. And the less operations, the better. So yes, Jane's algorithm is better, flat out. Okay? However, let's go ahead and say the same thing. In fact, let me, I want to hide it, what I do here. Okay. So we still got the same situation. We got Jane and Joe, but now we're going to zoom out, or we're going to look past it and see what happens. Bam. I guess Jane's algorithm has a bug, or just something happened. Okay? So now, as we can see, the tables change as the amount of data increases, because now this will go this way, and this will continue being that way. Okay? So, my question to you is now, which algorithm is better or faster? Joe's algorithm is better. Joe. Okay. So I would say that you do have to put what one of you said for more data, right? So now there comes a situation where it's no longer enough to just kind of give a generic answer, but now you have to say, okay, well, Joe's algorithm is better after you pass this magical threshold here, which might be like 200. But before that threshold, Jane's algorithm is better, right? It seems to be like this is no longer a linear relationship, right? This might be something like quadratic, maybe like a quadratic, or like log n times like n squared or something. Like there might be there's some non-linear thing going down here because it's going up. It might be exponential for all we know. There's something going on there. Whereas Joe appears to be pretty linear still. It's still linear. So whereas in the beginning, the big difference was that this was like a y-intercept of like 30, and maybe this is like, it's like an x. This one here, there's no y-intercept, but like it went that way, you know? So this happens a lot too. In fact, this might happen when you're dealing with something like your good old trusty bubble sort versus like quicksort. For really small amounts of data, your algorithm that's maybe not as efficient may finish faster than like something that requires like a lot of functions and recursion and overhead for like quicksort. So what I'm trying to make a point from this is two things. One of them, you have to specify a specific parameter when you are trying to analyze an algorithm, such as this. We call this one the N0, I believe. Something like that. You'll see when I put the definition in. Okay? You have to specify that value, like your minimum value that you're using to range something with. You're saying from this number and on is what we're looking at. We're ignoring anything before that because it's like a special case scenario, okay? That's one thing you have to specify. And the other thing is, it's not enough to just draw little pictures. We don't want, because like even if I draw this picture, like what is to prove that like this doesn't magically turn around and then this go up? Like what is to prove that doesn't happen? Plus, furthermore, we don't want to just base ourselves off of experimental data. We want to actually say like, okay, like I want to mathematically prove to you that Joe's algorithm will always have a linear relationship and Jane's algorithm is not going to be linear, and therefore Joe's is going to be better. Okay? That's something that I want to prove. And I want to prove it mathematically because, math rules in that sense. Like, then you can say something is experimentally good, but then you can't conclusively say that like the other parts you didn't check of that line are not going to change. Whereas if you say this mathematical relationship this line is following, then I can guarantee you that it will never go around. It's like limits and calculus and all this fancy stuff, okay? So we don't want to do calculus right now, so we won't do that part, but that's kind of what we're trying to do. We are trying to basically convert this into actual math functions. And that's going to be, when we talk about recurrence relations, what we'll be doing with that aspect. But before we do that, we want to do what are called boundaries. Okay? So let's go back to a single line. And we only got 2 minutes left. So we'll continue this on next week. Okay? Let's say that we have a line like this. Now let's be more realistic, especially if it's something like this. Okay? It could be something like that. What we are more interested in doing is, it's very hard to come up with a specific math formula for this one line. Like this will be some hardcore, you have to use like sine and cosine and just like a lot of quadratics to be able to do all this ups and downs probably, okay? Like this would be like x to like the 20th power. Like you'd have a lot of factors like that, just no, okay? So what we want to do is we want to create other lines. We want to create these like boundary lines at the bottom and at the top that are guaranteed to always have the entire function in there. We never want this to happen. We never want we don't want that because that defeats the purpose. What we want is we want to mathematically ensure that we actually have these lines. And then these lines are much simpler math formulas. This could be, again, like x squared. This could be x squared, but maybe with like 1/2 next to it. And yeah, okay, something like that. That's what we want to do. And these lines have a name. This is called big O, and this is called omega. And there's also theta. And that's what I'm going to talk about next week. I'm going to introduce you to what big O, big theta, and big omega are, which are these lines, and how we're going to mathematically define them so that we can contain this graph, this line. Because then we can say, we can use these much simpler functions to actually define how this graph will grow, and say, okay, it'll always be bigger than red, and it'll always be smaller than the orange. The bottom one is red and the top one's orange. I don't know if there might be colorblind people, so let me know, by the way, because I want to make sure I don't confuse you with the colors. So that's what I want to do. That's where that's the end game that we're going to get to next week. Is we want to be able to make these two lines, and we're going to call them big O and big omega, and then big theta, which is going to be the middle one. Why is it important to contain the graph? Because then now, if I create this O of n and omega of n, then these are numbers that I can actually use to compare my formula, my algorithm, with your algorithm. And then I can mathematically say my algorithm is better than yours, therefore I get all the millions of dollars because it's better. That's the end game. All of this is to see who's got the better algorithm. This is all about measurement. Because what will end up happening is when you do these things, you actually end up dropping the constant. So it turns out that this is just going to belong to the x squared asymptotic complexity. Okay? So that's the end game. We want to contain the graph because then we use those functions, those generalized functions, to compare this algorithm within the other algorithm. And that's what we're going to be doing. Every time I show you an algorithm, we're going to be looking at this asymptotic complexity of that algorithm, and that's how you know. So at the end of this class, when somebody comes to you and says like, hey, I have an O of n squared algorithm, and I have a log n log n algorithm, which one should I use? You automatically will say, well, you want to use the n log n, because that's way better than n squared, because n log n will have a growth rate that is much smaller than n squared, which means that as the data grows, the n log n is really going to outshine the n squared. But of course, if you find one that's linear, then you want to use that one. So that is the end game for why you have to learn this. And this is really, really important because, again, don't forget, this is all about space and time. And that space and time growth for both space is the same thing. You ideally want something that doesn't grow to like linear or logarithmic when it comes to space, like n log m space. You don't want something that like grows in like quadratic space, because like that's just going to like take so much space so quickly. You're going to be out of RAM all like in 5 seconds. So that's why it's all about being able to classify whether the algorithms are good or bad. Again, we are past this idea of like code works, we're good. No. Now we care about, okay, cool, code works, but like, is it actually fast? Does it take a lot of space? This is going to be what's going to be in your mind for the rest of the semester. Okay? So with that, I am going to call it a day. I shall stop the recording, but I will be here for, see, there's already people waiting in the 202. So yeah. Thanks for watching, everybody. I will see you next week. I'll stay here for a couple of questions, but I'm going to stop the recording for YouTube. So for those on YouTube, have a good weekend.